sampling distribution, and point estimation of parameters. Let us have some examples regarding the use of central limit theorem. Suppose that a random variable x has a continuous uniform distribution, f of x is equal to 1, or x is in between 0 and 1, it is 0 otherwise. And then suppose that a random sample of n is equal to 12 is taken from this population. What is the approximate probability distribution of x bar minus 6? And find the mean and variance of this quantity. So for a uniform continuous distribution, we have mu is equal to a plus b over 2, while the variance is b minus a squared over 12. So this would give us mu of 0 plus 1 over 2. So that is 1 half. And the variance would be 1 minus 0. So that's 1 squared over 12. So the mean of x bar would be still 1 half, while sigma squared of x bar would be 1 over 12 over 12. So that's 1 over 144. Now, for a probability distribution of x bar minus 6, so the probability distribution of x bar minus 6 would be expected value of x bar minus 6. So that's 1 half minus 6. So this is negative 5.5. So this is the mean of x bar minus 6. While the variance of x bar minus 6 is just the same as the variance of x bar. So the variance of x bar minus 6 is also 1 over 144. Let us consider another example. Suppose that x has a discrete uniform distribution. F of x is equal to 1/3 for x is equal to 1, 2, or 3, and 0 otherwise. A random sample of n is equal to 36 is selected from this population. Find the probability that the sample mean is greater than 2.1 but less than 2.5, assuming that the sample mean would be measured to the nearest 10. So the mean is a plus b over 2. So that is 1 plus 3 over 2. So this is simply 2. While the variance is, for a discrete uniform distribution, the variance is b minus a plus 1 squared over 12. Sorry, this is the formula. B minus a plus 1 squared minus 1 all over 12. So that is 3 minus 1 is 2 plus 1 is 3. So that's 3 squared minus 1. So 9 minus 1 is 8 over 12. So if we're looking for the probability of x bar in between 2.1 and 2.5, we must be getting uh, the probability of z equal to 2.5 minus 2 over square root of 8 over 12 is, I think, equal to square root of 2 over 3 divided by square root of 36 minus the probability that z is equal to 2.1 minus 2 over square root of 2 over 3 over square root of 36. So I think we can calculate this directly on our calculator. So the probability is 0.2311. Next problem. The amount of time that a customer spends waiting at an airport check-in counter is a random variable with mean 8.2 minutes and standard deviation 1.5 minutes. So mean is 8.2, standard deviation is 1.5. Suppose that a random sample of n is equal to 49. Find the probability that the average waiting time in line for the customers is less than 10 minutes. So we're looking for the probability that x bar is less than 10. So that is equivalent to a z value less than, so 10 minus 8.2 over 1.5 sigma over square root of n. So this would be a p of 10 minus 8.2 divided by 1.5 over square root of 49. So this is p of 8.4. So this is approximately equal to 1. So there is a 100% probability that you would be waiting more than less than 10 minutes if the average is 8.2 minutes. And for letter B, between 5 and 10, so x bar is in between 5 and 10. So this would, for 10 it is 8.4. So that would be P of 8.4 minus P of 5 minus 8.2 over 1.5 over square root of 49. So the probability of this can be computed using your calculator and using the statistical tables as well. So it's up to you to choose what method you're going to use. So I think this is also approximately equal to 1. And for letter C, the probability that x bar is less than 6. So that would be P of 6 minus 8.2 over 1.5 over square root of 49. So I think this is approximately equal to 0. Next one is the difference of two means. So for the difference of two means, if we have two independent populations with means mu1 and mu2 and variances sigma sub 1 squared and sigma sub 2 squared, and if x1 bar and x2 bar are sample means of two independent random samples of size n1 and n2, from these populations, then the sampling distribution of z is equal to x1 bar minus x2 bar minus mu1 minus mu2 all over the square root of sigma sub 1 squared over n1 plus sigma sub 2 squared over n2. This is approximately normal if the conditions of the central limit theorem applies. If the two populations are normal, the sampling distribution of z is exactly standard normal. So let's consider this. A random sample of size 16 is selected from a normal population with mean 75 and a standard deviation of 8. A second random sample of size n2 is equal to 9 is taken from another normal population with mean 70 and a standard deviation of 12. Let x1 bar and x2 bar be the two sample means. Find the probability that x1 bar minus x2 bar exceeds 4. So we're looking for the probability that x1 bar minus x2 bar exceeds. So that's greater than 4. So this is equivalent to a z greater than. So x1 minus x2 is 4 minus mu1 is mean 1 is 75, mean 2 is 70 all over square root of sigma sub 1 is 8 squared over 16 plus the second standard deviation is 12 squared over 9. So this is 1 minus a p of negative 0.22. So this would be a probability of 1 minus a p of negative 0.22. So this is 0.58706. For letter B, so we're just going to replace 4 by 3.5 and 5.5, and we're looking for the area in between. So for letter B, that would be the probability of, uh, for the upper limit, it would be 5.5 minus 5 over the square root of 64 over 16 plus 144 over 9 minus, for the lower limit, 3.5 over 3.5 minus 5 over the same denominator, 64 over 16 plus 144 over 9. So the probability is 0.17585. You can pause this and then practice working on this problem. So just to summarize sampling distribution, the probability distribution of a statistic is called the sampling distribution. For example, the sampling distribution of a sample mean x bar is the normal distribution. The simplest form of the central limit theorem states that the sum of n independently distributed random variables tend to be normally distributed as n becomes large. It is necessary and sufficient condition that none of the variances of the individual random variables are large in comparison to their sum. The formula that we use for sampling distribution of the mean would be z equal to x bar minus mu over sigma divided by square root of n for a single sample. If we are looking for the difference of two samples, the approximate sampling distribution of the difference in sample mean is given by this one. These are the references used for this lesson.